My name is Arnold Jacobson, and I'm fortunate that we have Tirthak and Patel here from Rice University. Tirthak is a local, so to speak. He got his bachelor's at the EC department, Electrical and Computer Engineering. So very proud to have you. He was a student in one of my courses, the EPIC. For those of you from EC, the EPIC 297, that all the students had to take. I don't teach it anymore. Anyway, so after his bachelor's, he went on to get his PhD at Northeastern and joined Rice University in 2023, where he's working on the intersection of high performance computing and quantum computing. He's leading the Positive Technology Lab there. And most recently, we got awarded the IEEE High Performance Computing 30 Career Award. Congratulations.
Thank you.
And please take it away.
Yep. Thank you, Dr. Jacobson, for the introduction. And thank you, CQIQC, for hosting me. Actually, 297 set me up for a path to pursue quantum and pursue the challenges that we do in our research these days. So as you mentioned, I'm an assistant professor at Rice, and my research mainly focuses at the intersection of high-performance computing and quantum computing, where we study systems-level problems in quantum computing. So to give a bit of an introduction, the question that we're asking in my group right now is, with practical quantum advantage still a few years away, what can we do right now at systems level to reason about lasting quantum utility? Meaning, in terms of the computer science and computer engineering perspective, how can we establish the technologies that we need in order to perform better when we do have quantum advantage? And to that end, we focus on the middle layers of the quantum computing stack, which aren't very clearly defined in quantum computing just yet. But generally, if we compare to the classical computing stack, it's the compilers, architectures, and then the operating systems way of things. And in that area, we have several works that focus on different kinds of technologies. So one is we focus on neutral atom compiling and architecture. So how we can schedule the atom movement, we can reduce the number of gates that are applied, and ultimately get better runtimes out of neutral atom solutions. And we work with Quera's technology there. Then we also focus on quantum machine learning in the superconducting space. The most recent work there has looked at federated learning for heterogeneous quantum clients, where there are different quantum computers of different sizes in the quantum clouds, and how we can perform federated learning in that space. And then we also look at neutral atom machine learning with the analog technology that Quera has. So we look at the Aquila quantum computer there. And we actually show that for certain types of generative tasks, we perform better than if they were performed on digital gate-based logic. Of course, scaling up this analog technology is harder, but certain types of generative tasks require very specific patterns that can be scaled up easily. Then we also look at superconducting compiling. Most recently, there's been this work about the transpilation of IBM's Qiskit-based gates. And we also focus on general cloud infrastructure and how we can optimize the runs and executions of these workloads in the cloud. And these are the two works that I'm going to be talking about today, which is how we can optimize all of the quantum computers that are available in the cloud space right now to improve not just the runtime or the fidelity, but also other systems level metrics like throughput, latency, queue times, etc. And so before I get into that, the key questions that we ask are, what are the unique challenges and opportunities of quantum computing clouds that don't exist in the classical cloud? And the first one is that multiple measurements or shots of the same quantum code are required for any given quantum circuit. And so that's a sample quantum circuit here, which is very small scale. And as we know, we run it and we get a probability distribution in a certain basis. It can be the computational basis or it can be other basis. And we actually have to run the same code multiple times to get this output. And that actually creates some challenges, but it also creates an opportunity to run the same code across different computers, create some sort of parallelism, which may not classically be available to us because the same code only needs to be run once. So that's an important factor to keep in mind. Another is that right now we have qubit noise variability in certain types of architectures, specifically superconducting qubit architectures. And that qubit heterogeneity stems from the manufacturing variability within the chip. And so that's expected to last even in the early fault-tolerant quantum computing era, because we'll have certain regions on the chip that, let's say, if we run a certain type of code, error correction code with a certain distance, we get a better logical error rate than other regions within the same chip. And so this kind of heterogeneous noise variability is something that really exists right now, but will continue to exist. So I have this picture where we have the connections that represent 2-qubit gate connections, and the circles represent the qubits, and the numbers that there are just showing different error rates of different qubits. And so in that case, I'm running U3 error, which is our universal 1-qubit gate. And what is the error rate of that? And then the CX is our 2-qubit gate on superconducting hardware. And we see that there are different error rates for different types of gates. And that's something that can become a challenge. But in these two works that I'm going to show, we'll look at how we can leverage that property as well to optimize our code. So the main sort of motivation is that when we run that circuit, ideally we get a certain probability of distribution in a certain basis. But now when we run it on an actual computer, depending on which computer we run it on and which region on the computer we run it on, we get different types of output fidelities. So here we have the ideal, which are the blue bars. And as we can see, we can map it to region A, or we can map it to region B. Region A here has higher fidelity. And so we see a total variation distance, which is just a metric of distance between probability distributions, that is lower than when we run it on map B. And so this is known as the circuit mapping problem. And this has been explored extensively with works going back to even 2019. So we're not going to focus on this particular problem, but we'll look at how we can leverage this to run our code in a better way. So here's the setup of the quantum computing cloud environment. Most of it looks very similar to the classical cloud. The user submits their quantum job, it gets queued, and then the dispatcher dispatches the jobs to one of the different computers. Currently, in some quantum clouds, there is the option to choose which computer you want to run it on, but that's not a scale-up model, so we anticipate that that's going to change in the near future. And we have these, and the cloud provider will make the decision for the user, just like we have for classical clouds, right? Classical clouds now have millions of nodes, and it's simply not feasible for the user to pick. They can pick the tier that they want to run on, but not the specific computer. And so similarly, we'll have a quantum model where we have different computers, and then there's the job dispatcher, which dispatches the jobs to different computers. And then the scheduler, based on the priority queue of the job, is going to schedule the jobs in certain order to run on the computer. And the additional step here that's different than the classical one is that we have the additional mapping, compiling, transpilation layer here, which does all of the routing that is needed to run the circuit on that specific computer. And the mapper also, in most cases, tries to optimize the circuit region where you want to run on the computer so that you get the best output fidelity or the lowest TVD. And then similar to classical cloud, once you have your probability distribution, it gets sent to a buffer, and then the user gets their output back. The difference here in quantum computing is that even if the computers are in the same tier, meaning they have similar specs, let's say they're all of the same size, they still have different properties just because of the heterogeneity of the individual qubits and the chip within the cloud. So an example of this is the IBM quantum computing cloud. At any given point, there are about 10 computers in the cloud, but each of them have different properties, different noise rates, and you can choose which one you want to run it on. Now, a common problem that is known when we do this kind of runs on a quantum computer is the temporal variability issue. So here we have a quantum circuit. This, I believe, is the VQE quantum variational eigensolver circuit. And we run it on 5 different quantum computers on the IBM cloud. And so these computers don't exist right now, but when we actually did this work, some of them were still there. And we see that depending on the computer that we run it on, we get different types of TVD. And that's even if we select a random map. The random map is basically I map it to any given region within the computer, or an optimal map, which is going to try to minimize this TVD. Simply the variability is so high among the computers that you can get different results. And then similar is the case with running on different days on the same computer. Here, we run it on the Hanoi computer. And we see that because of the daily calibration and the qubit drift that happens over time, you still get different performance on a daily basis. So it's impossible to just map to the best circuit map and get a consistent performance. And this kind of performance inconsistency is a big issue, especially if you're trying to run a workload which you're trying to optimize, right? Let's say a variational workload like variational quantum eigensolver or QAOA, where you want to optimize certain parameters over time. And in that case, you want each of the circuit that you run with different parameters to be similarly affected by the noise, so you can choose the best parameters. But if the noise are differentially impacting over time different circuits, it's sort of impossible to optimize it in this real space, even for algorithms that are intended for the NISQ era, for this near-term noisy era. We still want a certain amount of performance consistency in the fidelity so that we can optimize them properly. And so that's what this first work is going to focus on. It's about reducing this temporal, meaning over multiple days, and spatial, meaning across different computers, output performance variability on quantum computers. So the idea is that a user should just submit their job, and no matter what the day, what the computer, they should get similar output fidelity. Other metrics can vary, for example, how much time they have to wait in the queue, what kind of performance they're getting in terms of the overall service time, but you still want a consistent fidelity that a user would expect if they run this circuit.
So they not be standardized as the noise
in terms of the hardware? No, so that's the thing. So it depends on the kind of underlying technology. If we are looking at neutral atom clouds, then the qubits within the same computer do have homogeneity, just because the atoms are all homogeneous and have similar noise characteristics. Also although recently a work has shown that even there you get differential output based on where in the atom grid your atoms are situated, simply because the laser affects them differently at different locations. So even there might be some heterogeneity, but in the superconducting space, the qubits themselves are not possible to manufacture with a certain type of homogeneity, just because the silicon substrate, the chip that they're based on, will suffer from a certain level of variability. And so because of that, it's not possible to standardize that each computer have the exact same specs. Another issue is that with newer generations of computers, you get lower and lower noise on average across the qubits. But you still don't want to, throw away your old generation computers, which are just 1 year old. It's similar to, when you get new GPUs. And so typically these cloud environments just become heterogeneous, even in the classical space, because you have multi-generation of computers. And you want to still give a similar performance no matter what computer it was run on. And so because of these two aspects, you do continue to see variability, even if it's to a certain extent addressed in the hardware. Yeah. And so, yeah, so the goal is that users should see similar output fidelity regardless of when and where the code was run. And so this figure shows sort of different techniques that had been leveraged ahead of time. So the most common technique is to always map it to the map with the best TVD. So here I have a computer with only, I believe, 7 qubits, very small scale example, and I'm trying to run a 4-qubit circuit. So you figure out which map it can get the lowest TVD on based on the calibration statistics of your individual qubits. And then you try to schedule your circuit on that one. So that we refer to as the best map technique. Another one is that you have a given computer and you try to figure out what is the mean if I try to run all the shots equally across all of the maps, right? So now here we use the idea that I have to run the same circuit X number of times. So why should I just run it on one map? What if I average it out by running X over, let's say, 10? So I'm trying to run on 10 different maps, the same circuit. And that way I might get a more average statistic on my performance. And so the idea is to equally divide the shot across multiple maps on the same computer. You don't choose maybe the worst ones in terms of the TVD, but your 10 best you can choose. And that will sort of help you average out the performance. Because also remember, this is only for that day based on the qubit calibration statistics for that day. So just because a certain map has the best TVD on that day doesn't mean it will have the next day or even a few hours later on the same day. And the third issue is that if we do this equal division technique, different computers will still have different means. And so you won't get that standardization that we want, where the user can run on any computer and still get the same output fidelity. And so the key idea behind Anchor is to divide the shots intelligently across these maps such that you would see similar performance no matter what computer you were run on. So we do an optimization across K computers within the cloud. The user eventually only runs on one computer, but the optimization is done keeping in mind the statistics of K different computers to randomly, stochastically sort of average them out, and then eventually only run on the maps of one computer. And so the idea is that this is my fraction, and these A, B to M are different maps, and then these are different computers, one computer, two computer, the kth computer. And what I want to achieve is that the fraction of shots that I run on computer one on map A times the TVD that I get when I run on that map, plus all of these different shots that I have to run on that computer, should equal all of the other computers that I optimize over. So if I can achieve this, then I can ensure that the average TVD will be the same across all of the computer. So I'll repeat that again. The fraction of shots times the TVD on that particular map on that particular computer. And so, of course, all of the fractions on a given computer, because I'm only running it there, should add up to 1 times their average TVDs. And then across different computers, I should be approximately average. And so the overall execution flow looks like this. I'll explain the linear programmer part in detail in the next slide. But the user submits their circuit, and then out of all the computers, it gets dispatched to a certain computer. In this case, let's say computer 1. But the optimization is going to take place over all of these computers, just in terms of calculating what maps the circuit should be running on and what fraction of shots I give to each map. And so eventually I have these M different maps on each computer that I run my optimizer over. There's also this portion which will try to predict the TVD of the circuit just based on the circuit characteristics. That's a fairly simple thing to do because the TVD is very highly influenced by the number of gates in the circuit depth, types of gates, these sort of aspects. So simple machine learning model is actually able to do this prediction. And that doesn't actually collapse anything in terms of the quantum classical relationship because we're just trying to predict the final total noise in the fidelity, not the actual output distribution or the noise in each of the states. And then after this predictor does the predictor, it runs through the linear programmer to figure out the short division across the different maps on the selected computer. And then the fraction is established. You run them. You can run them in parallel. That's another optimization you can do. If your certain maps are disjoint from each other, those shots can be run in parallel. If they're not, then you serialize the other ones. And then finally, you send the output back to the user. So here's the linear programmer portion. So as I mentioned, I want the average TVD across all of my optimization computers to be approximately equal. And so I'm going to create this vector X, which is the fraction across all of the maps for all of the computers. So it's simply a vectorized version of all of these fractions. And then the C vector is going to be all of the TVDs that I predict for these maps. And I want to minimize C transpose X. It's a traditional linear programming setup, which is just trying to do the fraction times the TVD. If I minimize the total, then I'm minimizing each one as well. But within this, I have to add the equalization condition. And so here, X is my fractions. B is going to be the vector that I want to enforce my constraints over. And then A is my main equalization matrix. So the below portion here ensures that the equalization of TVD across all of the computers is the same. So I have these TVDs for one computer times all of these fractions, and they should add up to 0 because I want all of those to equal 0. And I do this for pairs of computers. So this is going to be doing computer 1 and 2, and then 1 and 2, but for map B, and then K minus 1 to K, 2, 3, 4, 5, all that is in the middle. And then we also have to ensure that the fractions add up to 1. And so that's enforcing this, that for each computer, this is computer 1, 2, 3, 4, all the way up to K. All of the fractions should add up to 1. And so this actually turns out to be a very efficient linear programming setup where in reality, even for very large computers, we tried for computers and algorithms up to 2,000 qubits, it solves within a second time because linear programming is extremely efficient. And for the actual TVDs, because we cannot enforce exact equalization, that might cause the linear programmer to fail in certain cases if the TVDs don't end up matching. We add a certain amount of approximation error epsilon just to ensure that there's a little bit of wiggle room. And based on how much similar you want this performance to be, you can set your epsilon. By default, we set it to about 10% so that the TVDs are within 10% of each other. Okay, so then the question is, how do we predict the TVD? As I said, it's actually a very simple machine learning model, just random forest. We generate a lot of random circuits, we get their characteristics, and then we simulate them under ideal and noisy conditions. And then we vectorize the simulation into form readable by random forest. And then we train a random forest model that would then be able to predict these TVDs for the algorithms that we actually test on. So we don't train this model for the algorithms that I'll show in our evaluation. We train them only based on random circuits, which are circuits with randomly generated gates and randomly generated depth Qiskit has that functionality where you can generate random circuits of certain sizes. And then we use them for training, and then we test on real algorithms. And for inference, all you have to do is provide the circuit. It will extract the features, vectorize them, put it in the trained random forest model, and tell you a predicted TBD. So before I get into the results, any questions about the design? Yeah.
Device to average case to be then choose the flip-flop, so and then not.
Yeah. Yes.
Or why not optimize with that device? So why don't you optimize with that flip?
Yeah, because I also want to ensure that, let's say, then I submit another circuit with different parameters, and then that gets dispatched to a different computer. So that's why I want to make sure that I optimize across these computers, so that if there's another circuit that comes in and that happens to run on a different computer, it still sees the same performance. So if I only optimize for that computer and figure out the fractions only based on that computer, I don't get the spatial variability reduction that I want, which is no matter what computer I run on, I should see similar performance.
Why do you want to?
Yeah, so we'll see in the results. So actually trying to get the best performance doesn't always give you the best performance, because what you're trying to do is figure out the best map at that calibration time for that given computer. Now, the issue is that, and calibration is a whole different issue, but calibration only happens once a day. So on IBM computers, it tends to be about at midnight, and you have to calibrate every single qubit because they have drifted during the daytime. And so it happens for about a couple of hours where each single qubit is calibrated. And if you run it right after, you get better performance because throughout the day, the qubits drift farther away from calibration. But you cannot calibrate more frequently because then you're just hogging the computer for calibration all the time. And so qubits are going to drift throughout the day, but there is nothing you can do about it. Now, because of that, and because the best mapping still uses the calibration data from hours earlier, it might not be the best, actually. And you end up getting worse performance, even if you try to do the best map, simply because the qubits don't have the same properties that they had at calibration time. And so we'll see in the results that best map actually not just has worse variability, but in many cases, even the mean TBD is worse because it ends up being not the best one. Yeah. Yeah. Yeah, so that's a very good question. So each computer, so we deal with 156 qubit computers here. And so there are combinatorially many maps based depending on the circuit you want to run. We choose, we run, so we choose like n number of maps, let's say. Let's say we want to deal with 20 maps. It's an arbitrary number that we choose. I believe we go with actually 20 maps. And 10 of them we choose randomly. So randomly, we go to different circuit regions and just pick 10 maps. The other 10, we run the best map algorithm. But every time you run best map with different attributes, with different compiler passes turned on, it still generates a different map region. And so we do, because it's a stochastic algorithm, actually. So we choose half of them using this best map algorithm, half of them using random, and then we plug them into our linear programmer. Then you can choose fewer. So even though we deal with 156 qubit computers, on real hardware, you can't really run circuits that large, simply because they just give completely random results. So I believe we were able to run off circuits up to 15 qubits or so. So we didn't have that issue here. But you're right. So if you have a code that is the same size as your computer, for example, then you have no mapping options. So in that case, we would extend this. We don't do it here, but we would extend this to then run the shots across different computers so that you divide the fractions across the different computers and get the different characteristics there. Yeah. I believe you have questions.
You know, the nice contrasted work. It's addressed on the individual groups.
Yeah, we have all of that data. So the data for this work is open source. We have all of that data for, I believe we did this over 2 months. And so we have all the data from those 2 months. It varies for each qubit. So it's sort of difficult to say like exact numbers, but it tends to be the decoherence times, for example, tend to be in about microseconds, 300 to 400 microseconds. The 1 qubit gate errors tend to be less than 1%, so 0.5% to like 0.01, 0.1%. And then the 2 qubit gate errors tend to be about 1% to 2%. And then the readout, which are measurement errors, tend to be 2 to 3%. And those trends have consistently been going down. So I've been doing this since 2019 or so. And at that time, even 1 qubit gates used to be at 1%. So in that time frame, they've dropped to about 10th of what it was 5 years ago or 6 years ago. And so they have been going down, but still it's considerable that you cannot run circuits that are the size of the computer itself. Yeah. Yeah.
I think how this really fixes temporal variability. It seems that they're still predicting the TDD and optimize whatever value.
Right. No, that is correct. So we are only optimizing with the calibration data of the computers at that time. But our hope and what we see empirically is because of that averaging, you still get reduction in temporal variability because some other computer has a different characteristic that might be similar to the same computer on a different day. So because we're using these same computers on the same day, multiple computers on the same day, we also see an effective reduction in temporal variability. Now, we could have used older data to also then do reduction in temporal variability, but we decided against it because just because you have, certain calibration statistics from prior days doesn't mean you'll also see them in the future days. And we were seeing a similar effect with just this multi-computer optimization. And so we just decided against it based on empirical results. Yeah. Okay. So in terms of the results, these are the algorithms that we evaluate. It's a long list of about 18 to 19 algorithms, but they're typical benchmarking circuits and also all of these variational circuits because we wanted to see the optimization effect. And these are the results. First, we're going to look at the TVD standard deviation, which is what is the variability in the TVD. Random map or random map is you run on any random map. Optimap is you run on the optimal map for that day. Equal distribution is if you, instead of calculating these fractions with anchor, you do the fractions equally across all of the maps. And then anchor is you select these fractions using the linear programmer. And as we see, in most cases, anchor has the lowest standard deviation of the TVD. And then, as I was saying, so this is the mean TVD, where we would expect Optimap to be the best because it's optimized for that day. But because of this calibration issue, it can also tend to be worse. And so we see that even in that case, equal dist and anchor perform better than Optimap. Sometimes even a random map is better than trying to optimize with the very best map. And these are, for each algorithm, we ran multiple runs over multiple days to get these statistics. And so this is my original plot that I showed in the motivation, but now this also has equal distribution and anchor added to it. And as we would expect, we see more stable results than with just choosing one map. So distributing these fractions, even if it is equally, is better than just running on the best map. And if you use Anchor to do this fraction aspect, then you get even more stable performance. So this is the temporal stability of the same data and then the computer-wide stability. So it's still not perfect because, as I said, we use that 10% wiggle room to make sure that the linear programmer doesn't fail, because we saw that if we don't do that, then in many cases, the linear programmer would fail and you don't end up with any fractions. So it's still better to use that wiggle room. And then these are just the compilation times. So as I said, in most cases, the linear programmer actually does sub-second times. The reason that these times are in second. The reason that Anchor has more seconds is because we have to run 10 best maps. So each of those will take sort of 10 times the amount of time that these do. But all of the transpilation is typically very fast. So even if it is a few more seconds, it doesn't really matter because the quantum time is what takes precedence over a few seconds that are spent classically to optimize it. And then we also ran these on the quantum hardware, and we ran it on all of the 5 computers that we mentioned earlier. The earlier results were noisy simulation because we did thousands of them. It's just not feasible to do them on real hardware. These are hundreds of runs that we did on the real hardware, and we see that we get better standard deviation, definitely better standard deviation because that's what we're optimizing for, but also a good mean as well. Okay, any questions regarding the results? Okay, so then I'll get to this. Yeah.
So how did we want to go for 10%, 5%? How much did the failure rate for the program go up?
That's a good question, actually. So we increased it percent by percent until we saw that for thousands of all of the runs that we did, there was 0 failure rate. But I don't know the exact numbers of what was the failure rate at each point, but I can get that number for you. But I really don't know, so I can't speak to that. So yeah, so in summary, Anchor tackles the problem of making sure that users get the same performance of regardless of which computer and what time they run on. Now, the next work is going to explore how we can make use of this device heterogeneity to actually improve performance for variational algorithms. And so that paper is called 3 Birds with 1 Stone, improving performance, convergence, and throughput with Nest. And so in variational algorithm structure, as many of you might be familiar with, we have a parameterized variational circuit that is trying to do some sort of optimization. So this could be the variational quantum eigensolver for quantum chemistry applications to find ground state of certain Hamiltonians, or it could be QAOA, quantum approximate operator ansatz, which also tries to run an unconstrained binary optimization on a quantum computer, or it could be some sort of quantum machine learning task where we have this parameterized quantum circuit that runs on the quantum computer, and its parameters are optimized classically. We refer to them as theta here, and then we get this expectation which we try to optimize over. So as you can imagine from our earlier mapping discussion, based on which map you run on, here, this is color coordinated qubits. It's just a sample, so it's not a real computer. But high fidelity here means these qubits have low error rates. Low fidelity means these qubits have high error rates. And depending on where you actually map your variational circuit, you see a different optimization map. So in this case, map 1 is really good. And so I'm getting a faster convergence and a lower energy gap to the actual ideal energy. And if I use a different map, then I get slower convergence and a higher energy gap to the actual ideal energy. And this was actually shown by a prior work called Concord, which is if you have, instead of classifying the qubits, you can classify whole computers as high fidelity computer or low fidelity computer, and you can map your VQEs to them and get better performance. And the way this classification is done is you look at the average error rates of different qubits. If you have a lot of high fidelity qubits, then you call it a high fidelity computer. If you have a lot of low fidelity qubits, you call it a low fidelity computer. And so the idea of this work called Concord was that what if initially, because the variational algorithm can get away with more approximation initially because it's not close to the energy gap. So what if we run initially this on the low fidelity computer, and then when it's closer to convergence, we move it to the high fidelity computer. And this solves the problem of no user really wants to run on the low fidelity computer. And so what if we do that? Then they can actually run on the low fidelity computer as well, and you get some amount of utilization in the quantum cloud, because what has empirically been observed in quantum clouds like IBM is that the queue times for these high fidelity computers are very high, and then the low fidelity computers are mostly sitting idle because no one wants to run on them. And so with this type of mapping, you can make sure that they also have some use case. But in our work, we actually extended it further with my collaborator who works in the classical machine learning space. And he noted that in classical machine learning, you can actually switch the precision of the model to get better accuracy for whatever task you're doing. So instead of running your model at the same bit precision, if you have different schedules of precision, it allows your model to jump from one local space to another and converge to a better global optimum. And so we thought that quantumly, we don't have any adjustment in terms of the precision, but we do have some amount of adjustment we can do in terms of the noise rate or the fidelity of the qubits. What if we have these different map spaces where we switch where the circuit is run over the optimization time and see what happens? Do we get better final convergence because we're forcing it to jump from one local space to another? This ESP here is a proxy for the TVD. And so the ESP being higher, well, it's one over the proxy of the TVD. So higher here is better. And so this map means over the VQE or whatever variational algorithm optimization, I'm trying to increase the fidelity of the map that I'm running on so that I get better ESP. And so we tried these different maps that are classically very well known for adjusting the precision. So you go from low precision to high precision. And we thought, what if we go from low ESP, meaning high noise or low fidelity computer, to high ESP? And so these are the results that we saw. This is the Concord result, which was where you initially run on a low fidelity computer, and then here the switch happens, you run on a high fidelity computer. But if you pursue more aggressive schedules, you see actually a much better convergence, much faster convergence, and lower energy gap to the ideal. And eventually, in this scenario, actually, the inverted ReLU is the best. And so that's the one we end up selecting. Even for other algorithms, we see that the inverted ReLU schedule is the best. And that is this schedule. So initially, we start on a low fidelity map. So you choose the worst qubits to run on, and then you choose better and better maps over your iterations. And then at around the midway point, you go to your highest fidelity map and then just optimize there. And as we see, so when we do that, we get these small jumps in our optimization space. And that's the algorithm jumping from one local space to another. For certain schedules, these jumps are too aggressive, so they're not good. But for the inverted ReLU, we find that they're actually really good because it helps them go out of these local spaces, especially if you're into a barren plateau, which is a big problem in quantum computers. This kind of switching can help you jump out of it. Yeah. Mm, So again, it actually stems, so that was, best map doesn't lead to the best one, and that was shown by this prior work, Concord as well. And the simple reason for that is, again, this calibration issue that I mentioned is if you just select the best map from certain calibration and then just stick with it, you're actually likely to end up worse than if you were to switch to these different maps, simply because the best map might not actually be the best. And there is no way for you to determine without doing another calibration, what is the best map? And so, yeah, that's the reason. And so we see that here as well. I'll sort of skim through this. This is the flat schedule with best map, and this is with inverted ReLU, which looks more messy because it's doing more jumping around, but finally it converges to a better point. And so another aspect of this work was jump versus walk. So you do have the option of jumping from one map to a whole different region, but that actually makes scheduling much harder if you're trying to do multi-programming and schedule multiple algorithms. So instead, we go with this walk option, which is over time, you change one qubit at a time, and you go from your lowest fidelity to your highest fidelity map that you can find. Of course, you don't always find close to what you want. So this is the ideal ESP map that I want. The first thing that has to happen is that it's discretized because I'm going from one region to another, changing every few iterations. But another aspect is that you're not going to be able to find maps without extensive combinatorial search that perfectly match your schedule. And so you have to deal with a little bit of approximation in terms of where you land up. And that's perfectly fine for our algorithm. And so here we see if we do qubit walk, it can be farther away from what we ideally want with this red line, but that's all right. And then, as I said, you can leverage this to do multi-programming, which is what we actually end up doing, which is you can schedule multiple algorithms to run on the same computer, and they're all sort of walking across this computer, switching their maps, and trying to do get the best results that they can. So these are results for VQE. These are the convergence plots for Concord, and then best map, and then Nest. And as we see, it's actually fastest and lowest energy gap. And these results show the same effect. Number of iterations, lower is better. Energy gap, lower is better. So ideally, you want to be in the, yeah.
I'm up to energy gas, but what is this in terms of like providers? It's like, we have like an energy gap that's like 10%, but of course, on tens of millimeters inside of that produce.
Yeah, these are all going to be larger gaps.
Yeah, well, how's that with 1%, like something that's like.
That I'm not sure. I'm not sure the chemical accuracy.
Because like,
I know that these are, so that result is still fine. These are really not good results. And that's just the underlying noise in the hardware is too high to do that. But we still try to sort of optimize and get the best that we can. And then here we see other metrics in terms of system throughput, where if we increase the program concurrency and multi-programming, what kind of results can we get? Of course, if we do 5x, we get higher system throughput, but it also reduces our chances of finding the best maps. And so beyond 4 on a computer of this size, which was 156 qubits, you'll see some degradation in the energy gap. And this shows the same results in terms of user cost. So here we actually try to project, this doesn't exist right now, that what if users were charged according to the fidelity of the computer or the map that they ran on? Because if the queuing times are larger for them, they should be charged more. And so in that sort of scenario, we wanted to test whether we can reduce the user cost instead of running on the best map, and we can. And largely, this is the results for QAOA. And again, we see the approximation ratio. So QAOA, we look at the approximation ratio, which here is larger with Nest. And the compilation times are very low here as well. It's going to be higher than Concord, which only has 2 maps. Again, it's the same challenge as Anchor, which is if you deal with multiple maps, then you have to compile multiple maps, route them. And so you do have more time for that. Oh, those are the VQE molecules from earlier. Those are the molecules that we're trying to find the ground state energy for. And so this is sort of the summary. They try to extract quantum utility out of the clouds that we have right now by getting more stable performance and by trying to use them to even get better fidelity in terms of the actual hardware runs. And the last thing I want to mention is, of course, my students who do all of the work, my PhD students, Claire, who led both of these works, and then Nick and Jason, and then our postdocs and undergrad students as well. And all of the code and data set for everything I discussed is on our GitHub page. So if you're curious about that, for example, the calibration data, you can download it from there as well. And that's it. Thank you.